All right. Good morning. It's 10 o'clock. Let us begin. So let's now take stock of what we have learned in this last three lectures, and then we will go a little forward for the remaining part in this last lecture. So we have seen that stars begin their lives as homogeneous gas mixtures of nearly 3/4 of hydrogen and about a quarter helium, and a small amount of heavier elements. So this is the composition that most stars have. And nuclear fusion occurs in the, just a second, let me go behind. So nuclear fusion occurs in the hottest region, which is the core. And stars spend most of their lifetime burning hydrogen in the core, where hydrogen nuclei, 4 hydrogen nuclei fuse to form one helium nucleus. And we have seen that the composition of the core is therefore altered. Started with 75% hydrogen and 25% helium, but it starts becoming more and more helium rich as more of the hydrogen gets converted to helium. Eventually, hydrogen in the core is exhausted and burning stops. Once the burning stops, then you are back to the situation that you were before nuclear burning started at all. So the core now will begin to contract under the influence of gravity. Now, by virial theorem, as the core contracts, it releases some amount of gravitational energy, and half of that goes into heating the material in and around it. So as the gravitational contraction proceeds, the gas will get hotter as the magnitude of E gravitation increases with contraction. So the gas surrounding the core, which earlier was not hot enough to burn hydrogen, now because extra heat has come because of the contraction of the core, the temperature outside has risen, and the material just outside the core can now become hot enough to burn hydrogen. So now you will have a situation where in the core there might be no nuclear fusion for a while, but just outside there is a shell burning going on of hydrogen. And then if the contraction proceeds long enough, then the temperature of the core will keep going up and up and up. At some point, it might ignite helium to go through the next stage of nuclear fusion. The 3 helium nuclei fuse to form one carbon nucleus, called it triple alpha reaction. But that requires a temperature which is at least an order of magnitude larger than the temperature required to burn hydrogen. So if the core contraction proceeds long enough, sufficient extra thermal energy is available to increase the temperature, then core helium burning will start. Once core helium burning starts, then it will, just like before, halt any further collapse of the core. So as long as helium burns in the core, the star will again be stable and spend the amount of time it takes to exhaust helium in the core. Once helium also is exhausted in the core, then again the next stage of core collapse will start and further thermal energy will be released. Now at this point, let us take a slight quantitative look at what is happening in such a situation. So the star now has a core envelope configuration. The envelope is relatively low density, core is relatively high density. There is a significant difference in density between the core and the envelope. The core let us say has a mass m and sub c, radius r sub c, temperature T sub c, and pressure P sub c. When there is no nuclear fusion occurring in the core, the temperature of the core is practically uniform. So the T sub c is the constant in the core. The surface pressure here is P sub c, and the envelope has its own temperature and pressure, but they meet at the surface of the core. So the envelope base temperature Te and the core temperature Tc must be the same for thermal equilibrium, and the envelope base pressure Pe and the surface core pressure Pc must be the same for mechanical equilibrium. Otherwise, there will be expansion, contraction at a rapid pace. So, if we're trying to see if such a structure can be stable. Now, the surface pressure of the core Pc and the interior quantities mass and radius can be connected through the virial theorem that we derived earlier. You remember the virial theorem told us that 4 pi r cubed P at r is equal to the sum of twice the thermal energy and the gravitational energy in the interior of R. So we can apply that here. Here we can put 4 pi RC cubed times PC is equal to twice E thermal plus E gravitational in the core. Now the E thermal can be written as the so we can then write PC by taking twice E thermal plus E gravitational and divide by RC cubed. And now I can take E thermal and write it as being proportional to Tc, because you can have a specific heat and specific heat per unit mass and the mass, so that this is the total specific heat, total heat capacity rather, times Tc. So that is the thermal energy. The C1 has absorbed the constants like 2, 4, pi and so on. Some constant times core mass times the temperature of the core divided by core radius cubed. That is the first term. And the second term is, as we know, the gravitational energy is proportional to minus g m squared by r4. So those numerical constants I have bundled up in this constant C2. So it's minus C2 mc squared divided by rc to the power of. The core surface pressure now has two terms. One that is proportional to mc divided by rc cubed. Other that is proportional to mc squared divided by rc to the power of 4. As you can see, the radial dependence of these two terms are not the same, and this will play an important role in deciding the fate of the core. Now we said that this pressure for an equilibrium must equal the envelope base pressure P. So envelope base pressure we can write as we have done before as Gm envelope squared. This is, the envelope has a mass capital M and radius capital R. So the base pressure of the envelope would be Gm squared by R to the power of. And by Virial theorem again, we have noticed that the temperature at the base will be proportional to m over r. So Gm squared by r to the power of 4, I can write r from the Virial theorem as m by t, because t is proportional to m by r, so r is proportional to m by t, and eliminate r from that. So r to the power of 4, I will write as m to the power of 4 by t to the power of 4. And I have Gm squared multiplying it. So finally, I will have the quantity which is proportional to T to the power of 4 divided by m squared multiplied by some constant. So the condition for support and equilibrium will be that these two pressures must equal each other. If such an equality is not possible, then equilibrium is not possible. Now what we notice is that because of the presence of these two terms, the Pc is not a monotonic function of R. So what I have drawn here is schematically the core pressure Pc as a function of Rc. When Rc is small, the second term dominates because it goes as 1 by Rc to the power of 4 rather than 1 by Rc cubed for the first term. And this being negative, it pulls the pressure down. And at larger values of Rc, the first term dominates, but as Rc goes up, again, because of this 1 by Rc cube dependence, the pressure goes down. So in between, the pressure reaches a maximum. And if you differentiate this and put to 0 and then find where the maximum is, you will find that the maximum can be written as some numerical constant C4 times Tc to the power of 4 divided by mc squared. So if we want to provide support and have a stable configuration, then Pc has to equal Pe, and this is only possible if Pe is less than the maximum value of Pc. For example, if Pe happens to be here, then you can find a equilibrium point here or an equilibrium point there but this is a stable one, this is an unstable one. So you will find the final solution over here, and this configuration will be stable. But if envelope pressure happens to be up here, then there is no intersection with the core pressure. So therefore, such a situation will not be stable. So this core envelope structure is stable only if PE is less than the maximum value of PC. Since the maximum value of PC is given by this and PE is given by that, this condition can be rewritten as the ratio of the core mass to the total mass of the star to be less than some numerical constants which we have derived from here, which works out to be 0.37 times the square of the ratio of the mean molecular weight of the envelope and molecular weight of the. So this is a number. It depends only on the composition. And Q is the mass ratio. So the mass ratio of the core cannot exceed a maximum limit. Typically, mu core will be about twice mu envelope. So this is a factor roughly about 10%. So this limit goes by the name Schoenberg-Chandrasekhar. This is not to be confused with the Chandrasekhar limit for degeneracy pressure supported configuration. But this is the Schoenberg-Chandrasekhar limit, which tells you how big in mass the core inside a star can grow before becoming unstable. So if the core mass increases beyond that, then core contraction will start, core collapse will occur. So now let us go back to the situation where you have a core which has stopped burning hydrogen because it has exhausted the hydrogen fuel, it's all become helium. Outside is hydrogen. The core has contracted a little, it's become hot, and the heat energy, excess heat energy released by the core because of the contraction, has heated up the exterior to the extent that hydrogen burning has begun in a shell. So you have the inert helium core, which is roughly at a constant temperature, that is isothermal. And then there is a hydrogen burning envelope around it. So initially, such a structure can be stable and hydrogen shell burning can keep producing some luminosity. But the product of this hydrogen burning is helium. And this helium product will then keep getting added to the core because that helium is not burning anymore. So the mass of the helium core will keep increasing because of the ashes of the hydrogen burning shell being added to it. So this ratio, mc over m, will continue to increase over time. And eventually it will cross this. And as soon as it crosses this, the helium burning core, the inert helium core will undergo a very rapid contraction until it becomes dense enough so that the degeneracy pressure support stops this quick contraction. So the star will make a rather quick transition from a thermally supported helium core to a degeneracy pressure supported helium. And that will cause a big change in radius of the core and a large amount of gravitational energy being released, which will heat up the exterior of the star. The star will rapidly expand because of this extra release of energy, which the envelope has to absorb. And this will drive the star up what is called the giant branch. So that's how the star will suddenly expand and become a large red giant. Now let's look at what all nuclear fusion stages a star can go through. We've already talked about fusion from hydrogen to helium, that is the main sequence stage. The next stage causes helium to fuse into carbon. 3 helium nuclei fuse into carbons. That is the primary reaction. And from carbon, if carbon burns, then it produces oxygen, and oxygen burning further can produce neon, magnesium, and silicon. And finally, silicon can fuse into iron nuclei, iron, cobalt, nickel, they're called iron peak nuclei. And beyond that, the binding energy per nucleon becomes lower. So therefore, there is no spontaneous fusion, or at least energy generating fusion that can occur beyond this. So the nuclear fusion in the core can only generate elements up to the iron peak. And as we will see later, not all of that is released outside the star either. They are even converted back in some of the more elementary forms afterwards. But will all stars go through all these stages of nuclear fusion? No. That is where the degeneracy pressure support of the core plays a very important role. Let's take a look at that. We have already encountered diagrams like this, so I will not elaborate too much. You have these gravity lines, which are in black for different masses, M1, M2, M3, M4, masses increasing this way. These lines have a slope in the log pressure, log density diagram of 4/3. Then you have these different temperature lines. So now I have drawn only those temperature lines which are the threshold of igniting different stages of nuclear reaction. So for example, hydrogen burning threshold is here. So once the star meets this line, you will get into main sequence. Once main sequence stage is over, the star will proceed along this line until helium ignites over here. And then when helium exhaustion occurs, it will again proceed along this line until carbon ignition occurs, and so on and so forth. Now, here we are talking about the core. So let's consider just the core mass. There is a maximum limit to the core mass which can be held by degeneracy pressure, which you also know. That is the point at which this gravity line becomes parallel and it touches the degeneracy pressure maximum. That's the relativistic part of the degeneracy pressure. So beyond that, there is no support possible. So that is the degeneracy pressure supported Chandrasekhar limit. But cores below that mass can be supported by degeneracy pressure eventually if it gets to this line. Now let us consider a core of this kind. It was burning hydrogen for a while. It was on the main sequence. Then once hydrogen burning is over, the core will proceed along this line. And as it proceeds, at some point it will hit the degeneracy pressure support. Now, if this degeneracy pressure support occurs before crossing the temperature where helium could have ignited, this core will never ignite helium because this support is eternal. So the star doesn't need to contract anymore to find support. It will be there forever. This will end its life as a helium white dwarf. It will never ignite helium. On the other hand, if the original core was a little more massive, then it will go through hydrogen bonding. After the main sequence, it will proceed this way. It will ignite helium and it will stay stable as long as helium is burning in the core. So that is going to be the helium main sequence. And then after helium exhaustion, the star will proceed again along this line and find degeneracy pressure support before it can ignite the next stage of it. So these objects will end their lives as what are known as carbon-oxygen white dwarfs. Cores more massive than that will cross both hydrogen and helium burning stages and may even be able to ignite carbon burning. Certainly, if it's able to cross this line, it will ignite carbon burning. But will stop before oxygen is ignited. They will end their lives as oxygen neon magnesium white dwarfs. Now, to ignite oxygen and to proceed to further stages of nuclear burning, it turns out that the core will have to be even more massive. And the core mass will now be in a state where degeneracy pressure support, by and large, will not be sufficient anymore. So cores more massive than this then will go through all the stages of nuclear burning, and then it will go through oxygen, neon, magnesium, silicon, and it will produce iron at the end. So as products, you can then expect these various types at the end of stellar evolution. You can have helium white dwarfs, you can have carbon oxygen white dwarfs, and you can have oxygen neon magnesium. Of course, there will also be configurations which will be degeneracy pressure supported hydrogen dominated configuration, which never ignited hydrogen. Those are the brown dwarfs. So they did not become stars, so therefore we will not consider them in the paradigm of stellar evolution. So in stellar evolution, we'll only consider objects which have at least gone through one stage of nuclear burning, and that is hydrogen burning in the main sequence. So they will leave either helium white dwarfs or carbon oxygen white dwarfs or oxygen and magnesium white dwarfs, or we'll proceed to all stages of nuclear burning and then we will see what happens. So have these different processes which give rise to different stages of products. Carbon fusion ends up primarily in producing neon. Neon then produces oxygen. Oxygen then produces silicon, and silicon then produces iron. What this diagram shows is the progression in the central temperature and central density of massive stars which go through these multiple stages of nuclear. So this is a model calculation, stellar evolution model calculation of a 20 solar mass star. So it goes through increase in temperature, little loop in temperature density, and then at this point, carbon burning starts. Once carbon is ignited, after that, it then proceeds to increase its central density until neon burning starts. Then it goes through these loops until oxygen burning starts. Then again, silicon burning starts, and then iron is produced. Once iron is produced, after that, there is no further nuclear burning at the center, so therefore, the core is not supported by thermal pressure, and it will continue to contract. The green line here is an 80 solar mass star, which does something very similar. And eventually, all of these lines will end up in this pink band. This one will go further and end up in the pink band. This green line goes and ends up in the pink band again. So what is this pink band? Now, the situation is such that an inert iron core has been produced because there is no spontaneous nuclear fusion that can occur in iron core. This does not generate any further energy. Around that, there is a silicon burning shell, which is producing more iron adding to the. Around the silicon burning shell, there is an oxygen burning shell, which is producing more silicon and adding to the silicon layer, silicon burning layer. Around the oxygen burning shell, there is a neon burning shell, which generates more of oxygen and adds to the oxygen burning. Surrounding that is a carbon burning shell, which is producing more neon and adding to the neon burning shell. Outside that is a helium burning shell, which is producing carbon and adding to this. And finally, there is a hydrogen burning shell, which is producing more helium and supplying the helium burning shell. Outside of this, there is no nuclear burning. So the core of the star has now this onion skin structure where you have shells upon shells upon shells upon shells doing various stages of. But ultimately, all of this is leading to more and more iron being produced and being added to the inert iron core. So the inert iron core is supported now partly by thermal pressure and partly by degeneracy pressure. But as more and more material, iron, gets added to the iron core, it gets squeezed further and further. The role of degeneracy pressure keeps increasing. But since there is nothing stopping it, the mass will keep getting added. And at some point, the inert iron core will exceed the Chandrasekhar limit. And once it exceeds the Chandrasekhar limit, there is no support that is available against gravity. Because gravity has won over now the degeneracy pressure support as well as thermal pressure support. So now the core will contract very rapidly. Now, as the core contracts, as I've already said before, it is going to release huge amount of gravitational energy, which will go towards heating of the core. The thermal energy will correspondingly increase. Half of it, half of the gravitational binding energy will escape the core. Half of it will go into increasing the temperature of the core. The temperature will now become so high that interaction of iron nuclei with the photons that exist over there will cause photodisintegration of iron. So iron nucleus was produced by nuclear fusion all the way from hydrogen. But now photons keep bombarding these iron nuclei and split them up. And they will split them up all the way to protons and protons, neutrons, and electrons. So all this work that was done by nuclear fusion to bind these nucleons into tight structures will all be undone in this phase, and the iron that was produced will get disintegrated into neutrons, protons, and electrons because of the enormous amount of radiation density that it will encounter in the very, very hot core. But there is no respite from gravity. So we have produced protons, neutrons, electrons, but the core will continue to contract. Its density will continue to increase. And as it does, the Fermi momentum of electrons will keep going up. The Fermi momentum corresponds to Fermi energy. So this Fermi energy will keep going up. So at some point, the Fermi energy of the electrons will become larger than the rest energy difference between proton mass and neutron mass. So at that point, it becomes energetically favorable for a proton and an electron to combine and produce neutrons. So as this core collapse proceeds, material will now become more and more and more neutron rich. So as this neutronization is going on, electrons, which were primarily responsible for producing the degeneracy pressure, are all getting gobbled up. So therefore, it is not just the relativistic part of the degeneracy pressure is unable to hold now against collapse. The source of the degeneracy pressure itself is disappearing. So the pressure is dropping very fast, and as a result, the core contraction will accelerate, and it will now contract in dynamical time scale, which for this density that it reaches at that point is only seconds. So within seconds, once you have reached this stage, within seconds, the iron core will collapse until the nucleon-nucleon repulsion, the repulsive part of the strong interaction force, is able to halt the collapse and produce a neutron star at the center. So that is a very large collapse from a core radius of a few thousand kilometers. It will proceed to a neutron star radius of about 10 kilometers. So the amount of gravitational energy released will be enormous, of the order of 10 raised to the power of 53 Earths. Almost all of it will be carried away by neutrinos that are produced in this process. But still, about 1%, or 10 to the power of 51 Earths, gets emitted in the form of radiation and kinetic energy, which is absorbed by the envelope. And this huge amount of energy, which is now dumped in the envelope, is much larger than the gravitational binding energy of the envelope. So once this energy is dumped, the envelope has no choice but to expand very rapidly in an explosive manner and get flung very far away. And this explosion is called a supernova explosion. And this mechanism of driving a supernova explosion is called a core collapse supernova. This core collapse supernova, typical energy budgets are 10 to the power of 53 ergs is what is released in the core collapse. Kinetic energy of 10 to the power of 51 ergs. And what is re-radiated from the envelope in form of photons is about 10 to the power of 49. Now you have produced neutrons over here and you have given them a lot of energy. So now these neutrons are zipping around at high speed, and these neutrons can be captured by other material which is around it. And rapid neutron capture, followed by beta decay later, produces much heavier elements than the stellar nucleosynthesis could produce at the core. So this is called R process, or rapid process nucleosynthesis, because it happens by rapid neutron capture. And that can give rise to all the heavier elements that we see around us. Although we know today that a larger source of heavy elements is the neutron stars that we produced at the center. And if two such neutron stars merge with each other, some amount of neutron-rich material gets expelled in the surroundings. And that neutron-rich material, when that undergoes beta decay, it can produce much of the heavy materials, particularly things like precious metals like gold, silver, platinum, uranium. So the composition that we see of those elements are largely explained by neutron star merger and the subsequent kilonovae. But many other species of heavy elements are generated in this rapid process nucleosynthesis, and that explains the amount of heavy elements which we have in the universe, which are still very, very small compared to the amount of hydrogen and helium we have. Now, in this stage, if the central mass exceeded Chandrasekhar limit by a significant amount, and then more and more mass got added because of fallback from the mantle of the star, it is possible to exceed the upper mass limit of neutron stars in the process. And if the total mass that eventually collapses has, has an amount which is larger than the upper mass limit of neutron stars, then the object will collapse straight into a black hole. And typically, if the initial mass of the star at main sequence was more than about 40 solar masses, then this is likely to occur. So there in the core collapse, you don't stop at a neutron star, but you go all the way to a black hole. And most stars have rotation, and in the core, as the core collapses, the rotation gets more and more enhanced because of angular momentum conservation. It keeps rotating faster and faster. And material around such a fast rotating black hole, which would be produced from it, can then be partly captured and partly expelled in very fast moving jets. And if you happen to be in the line of sight of such a jet, you can see a very bright gamma ray flash, which we call gamma ray bursts. So this core collapse is associated with both supernovae as well as gamma ray bursts in appropriate circumstances. So let's then summarize the key results that we have learned so far in this course of lectures. One is that the large majority of stars we see are in their hydrogen burning phase. Their lifetime is roughly proportional to 1 over the cube of mass. Heavier stars have lower density and higher temperature, and they populate the main sequence. The virial theorem told us that thermally supported stars get hotter and more compact as they lose heat. We also learned about degeneracy pressure. We know that it is of quantum origin, present even at zero temperature. Equation of state becomes softer as matter turns relativistic. Degeneracy pressure determines the extent of nuclear burning, whether nuclear burning will stop at hydrogen or helium or carbon or oxygen or neon or silicon or iron. It also provides long-term support to evolutionary end products like brown dwarfs, white dwarfs, and partly to neutron stars. The neutron star support comes partly from degeneracy pressure, partly from nuclear repulsion. And the heavier the configuration, the smaller it is. We also learned about the two limits of Chandrasekhar. Degeneracy pressure support not possible above a certain mass, about 1.4 solar mass per white dwarfs. And thermal support of stellar core not possible if core mass fraction exceeds about 15%. And then we saw mention of different end products. Here I have given the main sequence masses which lead to different end products. About 0.08, 0.5 solar mass leave helium white dwarfs, 0.5 to 8 solar mass leave carbon oxygen white dwarf, 8 to 10 solar mass leave oxygen neon magnesium white dwarf, 10 to 40 solar mass neutron stars, and above 40 solar mass black holes. So this is a summary of what we have learned about single star evolution. But in nature, there is also another factor that affects stellar evolution very significantly, and that is closed binary systems. I'll not go into the detail of it, but if you have two stars orbiting each other in a binary system, then their combined potential well looks like this, where there's a potential well at each of these stars, but there is also a bridge connecting the two stars, which is lower than the centrifugal barrier that you will find around the binary. So therefore, at some point, if the star grows large enough, material can move from one star to another. So basically, material can be stripped from one star by the gravity of other star, and the material can move from one star to another. So, for example, if you start with a binary system of 13 solar mass and 6.5 solar mass, at some point the 13 solar mass star evolves, its radius increases, goes to a giant phase, radius increases, and it's so therefore it climbs the potential well, and matter spills over into the other star. So this can then strip this star entirely of its envelope, leaving the core, helium core of 2.5 solar mass, and acquiring all that extra mass onto itself. So this can grow to a, in case of conservative evolution, 17 solar mass star. Evolution need not be totally conservative. Some mass could also be lost in the system, in which case this mass will be reduced. So this star started its life as a 6.5 solar mass star, but now it has become a 17 solar mass star. This 2.5 solar mass helium core will eventually undergo explosion and leave the 1.4 solar mass neutron star. The explosion will widen the orbit, and eventually some part of the helium star will also be captured by the other star. So you now have something like 17.3 solar mass star and 1.6 solar mass star. So you now see that a neutron star has been produced, and evolution has been completed of a 13 solar mass star, but there is a 17 solar mass star which was which is more massive than the original 13 solar mass star, is still not fully evolved. For single stars, I have said that the main sequence lifetime is proportional to 1 over m cubed. So the heavier stars must necessarily evolve earlier. But here, as you can see, the tables are turned because of this late mass transfer. You now end up with a younger, heavier star, and the older, less massive star has already evolved and produced a neutron star. And as a result of this kind of mass exchange, various changes happen in the evolutionary stages, and also in the expected mass of remnants. So I mentioned to you the different types of remnants that will be left by stars of different original mass. That corresponds to this red line, the primordial mass versus the mass of the remnants being produced, helium white dwarfs, carbon oxygen white dwarfs, oxygen and magnesium white dwarfs, and so on. In case of closed binaries, the corresponding line is over here. So if you start with a certain primordial mass, a single star, if no mass is taken away from it, will leave a heavier remnant than a star which is evolving in a closed binary system. So this correspondence between what was the original mass of the star that produced a certain type of product, that depends very much on whether the star was in a single system or it was in a binary system. By and large, most stars are in binary system, and if they are in binary system, how close binary was it? What kind of companion there was, and so on. So therefore, there's a whole range of initial masses that can lead to the product of a certain kind. All right, that is all of the lecture that I wanted to present to you. Let's stop here, and I can take a few questions. There should be time versus mass relationship, time versus core mass. Yeah, core mass continuously increases with time. So that will be related to the rate at which nuclear burning is occurring and the mass is being added to the core. It just keeps increasing monotonically with time. No, Q0 less, we'll get to here. If Q0 is greater than QSC, then the core will contract rapidly because the support is gone. The envelope, because of the energy that is now being dumped in the envelope, will expand. So whenever a core contracts in a star, the envelope expands. That's the kind of complementary relationship between the core and the envelope. Star going to a singularity means that if you have no support possible, then the mass will continue to contract until it becomes classically of zero radius. That is what is called singularity. But quantum mechanically, it need not be zero radius. It will have some structure over there. But classical singularity is just that. That if you have no support against gravity, gravity will squeeze everything to a point. Okay, so we'll go to raised hands. Safiq.
Sir, in the case of neutron stars, this
Yes.
neutron degeneracy pressure or the repulsive part of the strong interaction, which is more effective in, say, defeating gravity?
It is the sum of both, but I can give you an answer in the following way. If it was only the neutron degeneracy pressure that was available to hold up a neutron star, then the maximum mass a neutron star can hold would be 0.67 times the mass of the sun, which is below your white dwarf generation. That's called Oppenheimer-Volkoff. However, because of the existence of the nuclear repulsion, this mass limit is raised to about somewhere between 2 to 2.5 times the mass of the sun. So that is a substantial increase in upper mass limit, which means nuclear repulsion is certainly a dominant factor in providing support against gravity in neutron stars. Okay. So I hope I have answered your question. I'll put your hand down and ask Pushti to ask a question.
Yes, sir. Sir, in the case of closed binary systems, you told that there is one bond between the two stars. So, sir, it is related to space-time curvature. I mean, what is the meaning of that bond?
No bond. It is just the gravity. No? It's like between Earth and the Sun. Whatever bond exists between the Earth and the Sun, it's the same. There is nothing different. This plot is of gravitational potential, right? So potential is 1 over r. 1 over r has a curvature like that. And then there is another 1 over r which is nearby. When you join both of them, then you will get this kind of a curve of the total potential. One is this, the other is that. And then since this is in a rotating system, the binary is revolving, components are revolving around each other. So this is done in the center of mass coordinate in the co-rotating system. So you have also the centrifugal potential. So when you plot the total, then it looks like this. It's a plot of the gravitational potential. There is no physical connection. Okay, so let me take a look at. Yes, so there is no further question. I will close this. Take a look at any further chat messages. Yeah, the neutron star can accrete material. When the other star evolves, the neutron star will accrete some material. If the neutron star accretes enough material to push it over the limit, it will go to a black hole. So that can all happen. I have not taken it to the further stage when this star also evolves and starts transferring material back. Yes, I agree that in a binary star system, a small fish can eat big fish. No doubt about it. Okay, thank you very much. I think we will then stop at this point, and I hope you had something useful.